Now we have studied motion and we have studied various kind of forces which act on an object which is moving. But now we are going to study this force which is due to the medium in which we are moving. Okay, so this force is due to the medium in which the experiment or motion is being conducted. Now what is the meaning of medium? Like whenever we have thought about an object moving, we've always assumed that there is nothing around it. But now what we have to think about is what is around this object. Like in our case just now, it is air, nothing but air. So how this air will behave when this object will move, that is what is the resistive force. Now let us see what is our common experience in our everyday life. Suppose that if a person is standing and as this person is at rest, the air around is also at rest. So they are not acting opposite to each other or affecting in any way. But when this person all of a sudden, let's say that he is now moving in a bike maybe, and he starts riding in a bike, then this might be your common experience that all of a sudden the air it starts to blow. Okay? And you feel that as if the air is moving opposite to the direction of motion of the object. If this is the direction of motion, then it seems as if the air is blowing in the opposite direction. Now again, if this person he stops, let us say he stops, then again it seems as if the air doesn't move. It's not moving in any direction. So this means that the effect of the medium comes into play only when you're moving. So this air it's moving opposite to you. So it means that the resistive force which is due to the air is opposite to the direction of velocity. Like in this case, velocity is 0. So there is no opposition from air. So we say that the resistive force is also 0. But in this case, the velocity is not equal to 0. So the resistive force is also not equal to 0. So from here, now again if the person stops, so velocity again becomes 0 and the resistive force again becomes 0. So this means that the resistive force depends upon the velocity. If you are at rest in a medium, it doesn't matter. The medium will not oppose you or apply any force on you. So the first thing to understand here is that the resistive force only comes into play when the object is moving. And also, this resistive force is opposite to velocity. So we put a negative sign here. This negative sign just shows that R is opposite to V. They both are opposite to each other. Velocity is in this direction, R is in this direction. Or the force due to the air is in the other direction. Now we also have a constant here which is called, it is some constant, it depends upon the medium and the surface area. So this is how resistive force will depend upon velocity. But this is just one way of saying it. This relation is valid when the velocity is, in everyday life, it has a small value, like 40 kilometers per hour or 50 kilometers per hour. But if the velocity is high, if the person is moving with a high velocity, then r is proportional to v square, and it is given by minus d rho a v square. Okay, so this is valid when velocity is a high velocity, which is like a velocity of an aeroplane, which is approximately 900 km per hour, while here it is like 50 km per hour everyday life, or maybe 100 km per hour. Okay, so in these situations this relation will be valid, and in this situation when velocity is very high, then this will be valid. Now what is d? They are all constants, where d is called a drag coefficient. And now area is the density of air, and A is the cross-sectional area. Of the object. Okay, and this cross-sectional area is the cross-section along the velocity. So if something is falling down, then this will be the cross-section. If something is moving towards this side, then this will be the cross-section. Okay, so now let's say this is our first case and this is our second case, and let's try to understand them one by one. So let's talk about the first case first, this one. Okay, so it means that r is equal to minus bv. Let's try to understand this. Now it first of all, we just know that it behaves opposite to velocity and it depends upon velocity. Okay, now assume that something is falling on earth and it is falling with a certain velocity, and let us say that there is some object, and this object is falling on earth. Okay, and the medium, as you know, is air. It's falling through air. And let us say initially it starts from rest, so at time 0 velocity is 0, and it has a mass of m, and therefore if velocity is 0, r will also be equal to 0. So it is falling over earth, so it will be falling with force mg, and so it's a small, so there is no r here, so nothing is opposing it. So it's moving in air, but air is not opposing it. Okay, let us say now when time is 1 second. Now initial velocity is 0, so final velocity will be vf plus at. So it will be 0 minus gt. So the velocity will be, let's say we are talking about the magnitude, it will be 9.8 meters per second. This will be the velocity with which this object will move at time t seconds. Okay, so it has mg, but it has, so now r will be 9.8 times of v. So it means you have a small opposition from air. Let us say if the time is 2 seconds, then the object is moving with the force mg, and you have a larger r, and that r will be, if you put the value here, velocity will be 20 meters per second and r will be 20 times of v. So here it will be larger than this, so it will be 20v here. So it means that as the object is falling down, the resistive force will increase. But will it always increase? After some time they both will become equal. Okay, and if both of them they become equal, then at a certain time, let us say that at some time t, r will be equal to, because r is constantly increasing, so at a particular time it will become equal. So if it becomes equal, it means that acceleration will be 0. And if acceleration will be 0, velocity will be a constant. And this constant velocity is called the terminal velocity. Okay. So if we have to summarize this, it means that when an object is falling down, initially it has a larger mg and r is 0 if it is in some medium, let us say air. After some time, it has the same mg and a small r. After some time, it has bigger r. Okay, and then at a particular time t, this mg and this r, they become equal to each other. So r will become equal to mg. So when it starts falling from here to here, the velocity, when it falls from here to here, the velocity is increasing. But after a particular time, now the velocity will be constant. So if something is falling from on the ground, on earth, then initially the velocity will increase, after that it will become constant, and this constant velocity is what is called the terminal velocity. Now let us try to understand it and find some equations for this. So let us say that if some object is falling in air or in water, or you can take any medium you want to, and it is falling with a force mg, the resistive force will be opposite to motion. So because we are moving downwards, so resistive force will be upwards. And this is the total acceleration with which the object will fall down. So if we have to write an equation for this, it will be ma will be equal to mg minus r. Okay, and therefore now let's try to understand this equation. And initially when time is 0, the velocity is 0. When, let us say, time is any time t, velocity is any velocity v with which it is moving. And taking these conditions in this equation, let's try to solve it. So in this equation, acceleration we can replace. So let us say it is mg minus r. Now what is acceleration? Acceleration is nothing but rate of change of velocity. Now we're not talking about the time where the velocity is constant. We're just talking about any random time where the velocity is still changing or may not be changing. Let's try to find out a relation which can exactly tell you if it is changing or not changing. So we're taking any in-between situation where the velocity is still changing. Okay, so then it will be m dv upon dt will be equal to mg minus r. Now we know r is equal to minus bv. Now we are not using this negative sign, but we'll just write b into v. Why so? Because this negative sign just gives you the direction and nothing else. But already in our figure r is opposite to v. So we need not write this negative sign again and again. Because if I write a plus here, it will mean that mg and v are in the same direction. Mg and r are in the same direction, but that is not true. Mg and r are in the opposite direction, so we need this negative sign here. Okay, so now let's just try to solve this equation. So we just take this m to the other side, so it will be g minus bv upon m, and then take b upon m outside. It will be mg upon v minus v. Let's take this negative sign outside. So we can say that it is, first of all, let's take a negative sign outside. So it will be v upon m, v minus mg upon b. Okay. Now let us separate v and t so that we can integrate it. So it will be dv upon v minus mg upon b will be equal to minus b upon m into dt. Or so now v and t, they are separated, we can take an integral over it. Now integral over velocity is 0 to v, so it will be from 0 to v, and integral over time 0 to t. So now the integral of 1 upon v is log of v, so the integral will be log of v minus mg upon b 0 to v will be equal to minus b upon m 0 to t. So then this becomes log of v minus mg upon b minus log, just putting the value of v in 0, minus log of v will be equal to minus b upon m. Okay, I forgot t here, it should be t, so it will be t minus 0. So now we can take these logs together, so it will be log of v minus mg upon b. Okay, so here again I have made a mistake because it is integral over v, so it will be 0, so it will be mg upon b. Okay, here it should be minus mg upon b. I hope it is clear. And then just try to take v and t again separately. So it turns out to be log of v b upon mg with the negative sign plus 1 is equal to minus bt upon m. Okay, and then let's remove this log. If we remove this log, we'll get an exponential here, so it will be 1 minus vb upon mg is equal to exponential bt upon m. We can take the v and t terms separately, so then we can say that 1 minus exponential minus bt upon m should be equal to vb upon mg. So from here we can say that mg upon b 1 minus exponential minus bt upon m should be equal to v. So this is the expression we get. Now what we can do is, as you know that when an object is falling down, like we've already done, that initially the velocity increases and then it becomes constant. When it becomes constant, at that time r is equal to mg, and so we can make use of this expression, r is equal to mg. Now r is bv, so bv will be equal to mg. When this condition is satisfied, then we say that velocity is terminal velocity, and let us say that terminal velocity is vt. So from here bvt will be equal to mg. So vt could also be written as mg upon b. So this will be the terminal velocity, which is mg upon b. So now if we see this expression, so we can replace this by terminal velocity. So it turns out to be v is equal to vt 1 minus exponential minus bt upon m. So this is how velocity will change with time. As we've already discussed that first it will increase and then it will become constant and so on. So this expression will give you what is the value of velocity for each time. We can calculate from here. Now from our experience we know that if you have to plot time versus velocity, it should behave something like this. It should first increase and then it should be constant, as you know. Then when it is constant, then the velocity should be vt. Now let's try to use this expression and see if it works fine or not. And let's try to get the value of velocity for different times. So let us say if time is 0 seconds. So if time is 0 seconds, then v will be equal to vt 1 minus exponential 0. So velocity will be 0. So it means that at time 0 velocity will be 0. The point will be this. Now let us say that when time is maybe m upon b. So when time will be m upon b, v will be vt 1 minus exponential minus b upon m when time is so m upon b. Now this turns out to be 1 minus exponential minus 1. Now exponential has a value of 2.718. It is a constant. Put this value here, what you will get is, it will be vt 1 minus 1 upon 2.7. So it turns out to be 0.632 times the maximum velocity. So this time, at this time the velocity will be this much percent of the maximum velocity. This time is called a time constant. Okay, so at time constant tau, the velocity will be 0.632 times the time constant, the terminal velocity. Okay, and at infinite time, so let us say if time is infinite, then v will be equal to vt 1 minus exponential minus infinity. So it will be vt 1 minus 1 upon infinity. 1 upon infinity will mean 0, so it will be vt 1 minus 0. So v will be equal to vt. So at infinite time, velocity will be a constant, which will be terminal velocity. So that is correct, that at infinite time it will be a constant, which will be the terminal velocity. So this is how we find out the terminal velocity when an object is moving in some medium.